Daniel Smania speaking on deformations of one-dimensional maps.
Thank you very much. So I'd like to thank the organizers for the opportunity, and I'm very happy that you're celebrating Carsten. And we're a little too far away, maybe. I'm working real dynamics, and this is more like complex dynamics. So this is kind of a Trojan horse talk because it's more about real dynamics than complex dynamics. But there is a connection. I'm trying to use complex methods somehow in real dynamics. So I'm going to try to explain. So these are the content of most of this talk is in these two preprints that you can find in the archive. So there's many kinds of one-dimensional dynamical systems, especially real one-dimensional dynamical systems. You have a piecewise expanding maps, unimodal maps, multimodal maps, diffuse on the circle. We heard about this in the Misha talk, Jampolsky talk. Homeomorphisms of the circle with breakpoints. And now it's a very hot topic, interval exchange transformations and generalized interval exchange transformations. So what I find very frustrating is that, for instance, the last ones, except for the first one, all of these you have some kind of helaminization, for instance, but the methods that you use to prove rigidity in helaminization, convergence of helaminization operator, things like that, is kind of a very different from the beginning here. Unimodal maps and multimodal maps you use deeply complex dynamics. And in these other ones, you use real methods. And there is not a unified approach to this. So I'm not going to offer to you this today. But the long-term goal is to find methods that works for every kind of thing. Of course, I'm not claiming anything about this. But what is similar about all these real one-dimensional maps is that they are not strictly stable, but if you consider the topological class of these maps, pick all maps that has the same topological dynamics, this is, in many of these cases, a smooth manifold. Infinite dimensional is smooth manifold, but with finite codimension, okay? So just to give an example, if you pick like a tenth map, a map like this that is expanding, and you have the topological entropy, and the topological entropy is a complete topological invariant. If you have two these expanding maps, and they have the same topological entropy, so they are topologically conjugated, so the dynamics is given just by one number, the topological entropy. If you have a diffuse of the circle that have a rational rotation number and is smooth enough, then if you have two of these maps with the same rotation number, then they are topologically conjugated. So this also, the rotation number in this case is also a complete topological invariant. So they are not strictly stable, but it's so close to strictly stable as possible. Inside this infinite dimensional, finite codimensional manifold, they behave like strictly stable things. Okay? So that means that the formation theory of these maps is extremely rich, and that's, I think, is the difference between real one-dimensional dynamics and higher dimensional, or more two-dimensional, three-dimensional real dynamics. This is really specific for one-dimensional dynamics, and I'm trying to explore that. Okay? Okay. So the situation is like this. In many of these cases, you have rigorous results for some of these classes. There are some conjectures about others. So the topological classes often laminates the set of all possible dynamics. So if you pick one of these topological classes, this is like a Banach manifold. And if you pick two guys in the same topological class, there is a conjugacy between them. Okay? So that's very nice because you can talk about like smooth curves inside the topological class. For instance, this is like infinite dimensional Teichmiller theory, right? So you have many ways to represent geometrically, in a geometrical way, this topological object, this topological dynamics, and you can ask how the geometric fixtures of these dynamical systems moves when you deform this dynamical system inside this topological class. For instance, you can ask, you see something about this in the Benini talk. You can ask about the periodic points, how they move when you move in a smooth family inside the topological class. The multipliers, what happens, the invariant sets, the invariant measures. This is something that I work with Viviane Baladi a lot. So there are many questions you can ask. It's exactly like Tashmili theory. You have some many ways to geometrically represent a topological, a compact, for instance, compact topological surface has a hyperbolic Riemann surface, and when you move a curve inside the Tashmili space, the length of the closed geodesics changes, and you wanted to see what happens, right? It's the same, exactly the same thing, but it's infinite dimensional Tashmili theory. Okay, so the question, what I'm proposing, is to provide a general method to show that the topological classes are finite dimension smooth manifolds. Okay, so what's the blueprint? This is, of course, inspired by, don't need to explain this, is inspired by holomorphic motions in complex dynamics. So suppose that you have a family of maps where you don't have bifurcations. Everybody is the same topological class. So there's a family of conjugacies between these maps, okay? And turns out that often this family of conjugacies moves with the parameter in a smooth way, okay? So you see in Anna Bedini talk about J-stable rational maps, for instance. In this case, the periodic points are moving. They're dancing in a synchronous way inside the complex plane, okay? So it's the same thing happens in other situations, and this is smooth. That means that you can differentiate this with respect to the parameter t, not with respect to the x, okay? You cannot differentiate in the phase space. Usually the conjugacy is very bad, it's singular with respect to the Lebesgue measure. Okay, so if you differentiate that, I'm not doing the calculation, but if you differentiate this family of conjugacies with respect to t, you can find that the conjugacies, this family of conjugacies, satisfies this ordinary differential equation here, okay? And turns out that this alpha t that defines this ordinary differential equation is a solution of this cohomological equation here. So suppose you have a family of deformations. You don't have bifurcations in this family ft. So the family of conjugacies satisfies this ordinary differential equation, and you can usually calculate the alpha t a priori. So you don't need to know the conjugacies to calculate alpha t, okay? So the idea is try to reverse this argument. Suppose that you have this for a family ft, and for every t, you have a solution for this cohomological equation, and is nice enough in such a way that you can reverse this argument, okay? So suppose that for every t, so suppose now to have a family, you don't know if this family does not have bifurcations. It's the same topological class a priori, but suppose that you can find for every t a solution for this cohomological equation, and this solution is nice in such a way that this ordinary differential equation is uniquely integrable, okay? I'm going to give some examples of that. So in this situation, you can integrate this ordinary differential equation and find a flow, and this flow gives you the conjugacies. So you can reverse the argument, okay? So under this situation, you integrate, you get the family of conjugacies. So, the idea is the following. So suppose you wanted to prove that the topological classes are manifolds with finite codimension. So the idea is to characterize the tangent space of this topological class at a point f0, has the set of all vector fields V that has a nice solution for this cohomological equation, okay? And then once you have that, the solution is regular enough, alpha t is regular enough to be able to integrate this and get the conjugacies. Okay? So that's the sketch of the thing, and this, of course, is based on holomorphic motions and ideas in complex dynamics. I'm going to give the reference soon. Okay? So the main motivation is the work of Mitchell Lubitsch on hybrid classes for quadratic-like germs. Okay? Hybrid class is not exactly the same as topological classes, but I'm not going to get into the details here. So if you are in the same topological class, then hybrid class you are in the same topological class. The other implication is not actually true in general, but in the interest cases, for real maps, for instance, it's hard work, but you can prove that if they are in the same topological class, they are in the same hybrid class often. Okay? And there are also other works. Mitchell and Polsk make reference to this work before. Hisler proved that the topological classes of real analytic diffeomorphisms of the circles satisfying the Bloom conditions are actually manifolds. Okay?
Doesn't he require that these be close to a rotation?
Sorry?
In Rissler's work, doesn't he require that they be close to a rotation?
Maybe you're right. It's a perturbative argument, right?
Because I think there's more to do.
Yeah. You're probably right. Sorry. Yeah, you're probably right. Yeah. Okay, so let me say something about ODEs that you probably learned in your first course on ordinary differential equations. So if you have a equation like this, and alpha t is Lipschitz, you can easily prove that this is, you see, everybody see this in the first course of ordinary differential equations. This implies that this has a unique solution, okay? But turns out that you can weaken this assumption. For instance, if you weaken too much, you don't have uniqueness, like continuous or holder. But if the alpha t is like Zygmunt or log Lipschitz, then you have unique integrability of this ordinary differential equation. And these are the two cases that I'm mostly interested in, okay? So, as I said, for continuous and holder, you don't always have unique integrability. For Lipschitz, you do have continuous integrability, and the flow is actually Lipschitz. But this is not a very nice solution because situation, because in this dynamical setting, alpha t is very rarely Lipschitz. It's not even bounded variation. It's really bad. Okay? So the situation that I'm most interested in is in the Zygmunt situation and in the log Lipschitz situation. In these two cases, you can have some results in the 70s, I guess, for log Lipschitz and Zygmunt, where if alpha t, for instance, is Zygmunt, then the flow is quasi-symmetric. It's quasi-symmetric, and you can have some estimation about the quasi-symmetric symmetry of the time t flow or the time t map. Okay, and if alpha t is log Lipschitz, then the flow is holder, and you can have an estimation about the exponent, holder exponent, and also the constant in the frontal of the holder expression. Okay. Okay, so now I wanted to do some connection that you are going to find very, how you prove that? How you prove that the solution of this cohomological equation is actually Zygmunt, for instance, or log Lipschitz, okay? So in the complex dynamics, you have some very clever tricks by De Mello, Lubitsch, De Mello, and Avila, so call it infinitesimal pullback argument, that allows you, sometimes you prove that this solution alpha is actually a Zygmunt. But here, in one-dimensional dynamics, you don't have this kind of technique. So what I wanted to do? So what I'm going to do is derive this in a formal way. So if you derive this with respect to x in a formal way, you can see that the derivative of alpha t satisfies this cohomological equation that you see here. And if you solve this in a formal way, again, you see that the derivative alpha should be this sum. It's like a Birkhoff sum of some observable. And this observable is right there. Okay? So you just cannot, you can do that just in a formal way because this is actually not a function, right? This is actually not a function, but it is a distribution. Okay? So I'm going to prove that this is a nice distribution, and this implies in some situations that alpha is regular. Okay? Okay, so that's the main problem. If you wanna to, you can just forget everything that I said. What I'm going to do now is I have this cohomological equation, and you have Ft, some dynamical systems in the real line, and you have some V, a vector field, and I wanted to find alpha a solution for this and to prove that the solution is regular enough to do my business, okay? So it's the usual thing. Instead of, say, understand topological classes of maps, you prefer to understand ellipse vector fields, ellipsis fields on your dynamical system. So you internalize the problem, right? So instead of looking for the topological class and the tangent space, you just look for the solution of this cohomological equation and study this cohomological equation. Okay. So let me just first give you some toy model. Expanding maps of the circle. I know that's a very trivial dynamics. You know a lot about this dynamics in many points of view. But it's a nice example that even in this case, for expanding maps in the circle, this can be tricky. Okay? So suppose you pick a C2 plus beta expanding map of the circle, and V, a vector field on the circle that is 1 plus beta, okay? So it's extremely easy to prove that there is a unique bounded solution for this, and this is continuous. It's an exercise to prove that. But turns out that you can, to understand the regularity of the solution alpha for this equation, Amanda de Lima proved something very interesting that relates this difference with the Birkhoff sum of this observable here. Okay? So the statement is a kind of a little technical, but let me give you a more clean version of this. You have something like this. Suppose you wanted to understand the regularity of alpha. That's what you wanted to know. You wanted to know if it's Lipschitz, if it's Zygmunt, if it's log Lipschitz, or something like this. So to do that, you need to study this quotient here. Okay? For instance, if when delta goes to 0, this converges to some number, then alpha is differentiable at x. Okay? Or if this is bounded, so alpha is Lipschitz. So understand this is understand the regularity of alpha. But the other side, what you see is a Birkhoff sum of some observable, some function. And this is one of the main objects in ergodic theory. And that's what's interesting, because okay, these dynamical systems like expanding maps on the circle or on the interval are extremely complicated. They have like, it's like a Julia set of a rational map. You have a density of repealing periodic points, and you have orbits that are dense in the phase space and things like that. But the ergodic theory of these dynamical systems are extremely well known. Okay, so you have invariant, you have physical measures with nice properties and so on and so forth. So the right-hand side, we understand a lot. You understand a lot about these Birkhoff sums. So you can use that to understand the regularity of alpha. Okay, so I like this one, so I'm going to put a heart. Okay, just to have, this is one of the main things: the connection between ergodic theory and this problem of deformations of dynamical systems, what surprised me a lot in the beginning. Okay, so one consequence of this is quite simple, actually. You can prove that one line using the previous slide is that alpha is always a Zygmunt function. Okay, Zygmunt functions are quite special because if you pick what's called a quasi-conformal vector field that's real in the real line, so this vector field is Zygmunt. So they are kind of important, and in particular, they implies the unique integrability of this ordinary differential equation. Okay, but this is the best you can do, even in this very simple toy model. So if you pick an expanding map of the circle, F is some V that's regular enough. Either alpha is C1 plus beta, or is nowhere differentiable. So there is a dichotomy between the two cases. And what is really nice is that the first case is extremely rare, as you're going to see. And so this case is actually genetic. So for most of the cases in the topological point of view, alpha is nowhere differentiable. It's like the classical Weierstrass function that you see in the course, in analysis course. And this is a little more technical. I'm not going to explain everything, but these 4 statements are equivalent. So if you know something about this multi-ergodic theory, probably you saw B, C, and D are equivalent. And turns out that alpha is nowhere differentiable, for instance, if only if this sum, this finite sum, is different of 0 for some periodic point. If you find just one periodic point where this sum is different of 0 for this observable phi, then automatically alpha is nowhere differentiable. So this is a checkable condition. You can check this. For instance, let me give you an example of this right here. So you pick the angle doubling map on the circle, for instance, and you pick v equals to this simple trigonometric function. So you can easily check that the solution for this homological equation is given by this series here. It's easy to see that this is continuous, and this is actually the classical Weierstrass function that you see in the course of analysis course. This function is nowhere differentiable. And you can prove that in one line using the previous statement, because 0 is a fixed point for this angle doubling map, the angle 0, and phi, this observable here, is different of 0 at 0. So automatically, you can conclude that alpha is nowhere differentiable. So there's a classical result that you can prove using this dynamical argument. So that's I like this a lot. Okay, another thing that you can be more qualitative about, okay, you can say, okay, it's nowhere differentiable, so it's hopeless, you cannot understand this. But you can actually be very precise about the regularity of this solution alpha for this homological equation. This satisfies some kind of central limit theorem. Okay, maybe you don't like these statistical results, you're not interested in that, but a corollary of this is that this alpha is not Lipschitz in any set with positive Lebesgue measure. Okay, if you pick every set of positive Lebesgue measure on the circle, this alpha is not Lipschitz. So it's really bad. It's not really Lipschitz at all in any sense. Okay, it's not even bounded variation. Okay, it's not even bounded variation function. Okay. So there are many previous results about this kind of regularity of alpha. As I said, the main influence is Lipschitz work in complex dynamics for quadratic-like maps. We wanted to understand the hybrid class of quadratic-like maps. But we also have some results with Viviane Baladi to understand families of topological classes of piecewise unimodal maps. You have unimodal maps, 2 branches expanding, and you wanted to understand the topological class of these maps. And we have well, it's not so recent anymore, about continuous solution for the homological equation in the case of Kohler-Ekman maps. So these are maps with critical points, Okay, some recent results. This is for piecewise expanding maps, so you can have discontinuities. You can have many branches and discontinuities. So the main technical, this result is kind of technical, so I'm going to clean this for you here. So suppose you have V that has a continuous solution for this equation, this homological equation, where F is a piecewise expanding map. So it turns out that the derivative of alpha makes sense in the sense of distributions. And this derivative is a bounded function, so that's the boring part of this decomposition, and this Birkhoff sum. Okay? So this is not, again, this is not a function. If you pick some phi, typical phi, this certainly diverges for almost every point. Okay? So this is definitely is not a function. But in the sense of distributions, this makes sense. And let me explain to you what I mean by distribution. Distribution in the sense of Schwartz. So again, this distribution tells something about the regularity of alpha. And the other side is about ergodic theory. So it's a connection between ergodic theory and deformation theory.
Does phi have average theorem for invariant
Yes, when there is a continuous solution for that equation, phi is always zero average, yeah, with respect to any invariant measure of the map. Okay, so you have this, this picture. So what I mean by this is the derivative in the sense of distributions. So I mean in the sense of Schwartz, okay? So suppose you have like a compact manifold, could be an interval with borders. And consider the the space of C-infinite functions, the best functions that you can have in this compact manifold. So a linear continuous functional in this space is a distribution. So this was defined by Lawrence Schwartz, and it's basically the language that PDEs and harmonic analysis is writing, okay? Okay, so there are many examples of this. So for instance, pick the Lebesgue measure, you pick F and integrate with respect to Lebesgue measure. This is a distribution. A measure that has some absolute continuous with respect to Lebesgue measure, or density G. This is also a distribution. Another measure, regular measure, is also a distribution. But you can pick something more weird like this. You pick F and associate the derivative at some point plus the third derivative in another point. So this is not a measure anymore. It's not. It's kind of a more exotic, but this is a distribution. Okay. So if you have a dynamical system with an invariant measure, and suppose that is strongly mixing. So that means that this limit of 0. This means basically that events that are distant in the future, from the present in the future, are almost independent with the present, with events in the present. Okay. So suppose that is strongly mixing. If you have this assumption, I wanted something additional to this. I wanted this to have exponential decay correlations. This is the best you can get, usually in dynamical systems. Like expanding map of the circle has exponential decay correlations, a Nosov map has exponential decay correlations, and so on and so forth. Okay? So suppose you have these exponential decay correlations. So you can, let me skip this. So what you can do is define a distribution in the following way. You pick some C-infinite function and just multiply here G by, you fix some map F that is, let's say, bounded, and take this series. So because you have exponential decay of correlations, this converges, and you associate to each C-infinite function a number. And this is a distribution, okay? So it turns out that the distribution that I show you is exactly this kind of distribution. If you have a Birkhoff sum of observable here, you can take this distribution here. And so to each observable F, you can associate a distribution. So that's what I mean, that the derivative alpha is a distribution, is exactly in that sense, okay? And then you can ask about the regularity of this distribution. How regular is this distribution? If it's really a function or maybe a measure or something more complicated. Okay. So in one-dimensional dynamics, real one-dimensional dynamics, you can do something that maybe make you more comfortable. Instead of looking for the distribution, you just integrate the distribution in the interval 0, 1. When you do that, you get a function. For every x, you associate this integration of this distribution in this interval 0, 1. So instead of looking about the regularity of the distribution phi, you can ask about the regularity of the function alpha. There is a connection between them, okay? Of course, in this case, the distribution should be defined in bounded variation functions, for instance. But that's usually the case for piecewise expanding maps. So don't worry about that. So you can ask about the regularity of alpha. For instance, if alpha is Lipschitz, that means that the distribution is a C-infinite function. Okay? That's just one example. Okay. So let me skip this too. So what I wanted to, so that's one of my favorite things too, is the following. If you wanted to understand deformations of these dynamical systems that are very complicated, like piecewise expanding maps, this is equivalent to understand primitives of Birkhoff sums. So if you understand the regularity of these alphas that you are writing in this way is the same that understand the regularity of alphas that satisfies these cohomological equations. So that's maybe is the main thing in this talk. Connect deformations of dynamical systems with ergodic theory of these dynamical systems. So one consequence of this result we call Ragazzo is the following. Suppose you have a piecewise expanding map, and you have a continuous solution for this equation here. So automatically, this solution is log Lipschitz. So this implies, in particular, that this differential equation is uniquely integrable, and you can get the conjugacies using this ordinary differential equation. So a corollary, well, a consequence of this is the following. Pick a piecewise expanding map, let's say C3, okay? Pick all the piecewise expanding maps of class C3. So if you pick some F0, you consider all the maps has exactly the same topological dynamics that this map. So this is the topological class of F0. So the topological class of F0 is a Banach manifold, and the codimension with finite codimension, and the codimension is just given by the number of discontinuities of F0. So for instance, if you have a map like this, so how many discontinuities you have this? You have one discontinuity here of the derivative, right? One here and one here. You have 3. So using this formula, you get codimension 4. You have codimension 4, okay? So in this case, the codimension of the topological class is 4. And you can characterize the tangent space of this Banach manifold has the subspaces of all V's that satisfies this, has a continuous solution for this cohomological equation that you see here. Okay? So this is similar to the result of a little bit for quadratic-like maps. In this case, the codimension is 1, but in the complex setting. Okay? Okay. And another consequence of this is that if you have a smooth family of piecewise expanding maps where you don't have bifurcations, everybody is topologically conjugated with each other, then the conjugacy is Holder continuous. This is already known. But what's interesting is that you can estimate how close to identity this conjugacy is. Okay, so you can the exponent is beta Holder, where beta is closer and closer to 1, and you can estimate that in terms of the solution of the cohomological equation. Okay, so I didn't told you so much about this observable. I show you this phi that appears in all these statements, and it's kind of ugly, but it's related with the Lyapunov exponents of the orbits. So suppose you have a family of dynamical systems, and you don't have bifurcations on this. So all the periodic points are moving, dancing in a synchronous way in the phase space. So suppose that X is a periodic point, for instance, and you have the analytic continuation of this periodic point, and you can calculate the Lyapunov exponent of this orbit. When you derivate this with respect to t, what you get is exactly the Birkhoff sum of this observable here. So this observable is telling you how the geometry of the map changes along the family. Okay? How the geometry of how the Lyapunov exponents of the invariant measures change, and so on and so forth. Okay. Another thing that's interesting, and that is in this case, is not always the case that the topological class coincides with the quasi-conformal class or quasi-symmetric class of the maps. So that's something interesting, because you can have a discontinuity, and in the right side, this discontinuity goes to a periodic orbit, let's say period 3, and in the left side, you convert to other periodic orbit of period, let's say 5. Okay? So the Lyapunov exponents of these two orbits can be completely different. Okay? And turns out that this quotient of the Lyapunov exponents is a quasi-symmetric invariant. It's really easy to prove that. I didn't find in the literature this, so I give you the statement here. You have two maps that are conjugated by a quasi-symmetric map. So the correspondent quotients of the Lyapunov exponents are exactly the same. So that was a little surprising for me. And this implies the following.
Sorry, what was the setting? C is what?
So C is a discontinuity for the map. So you can have like a discontinuity like this. Okay? So in this case, when you have discontinuities, you have this no-trivial quasi-symmetric invariant. And it's easy to change this invariant in the topological class. It's not very complicated. So suppose that all discontinuities of your map are eventually periodic on the right and on the left. Okay? Then the quasi-symmetric class is actually an embedded submanifold with finite codimension inside the topological class. So you have the topological class. Inside the topological class, you have a submanifold also with finite codimension. And this is the quasi-symmetric class of this map. And turns out that you can choose, give examples where the codimension is positive. Okay? So that's the picture that you can find in some examples of this. So if you get topological class of F, it's a Banach manifold, and the quasi-symmetric classes foliates the topological class. So they're really different. Okay? So they're really, really different. And what is nice is that the tangent space on F of these submanifolds is characterized by the solutions, the regularity of the solutions of this cohomological equation. For V's where the solution is log Lipschitz, you have the topological class with the tangent space of the topological class. When alpha is Zygmund, you have the tangent space of the quasi-symmetric class. Okay? Let me just say that I don't have any examples. For instance, suppose the map does not have discontinuities, like this one. I don't know in this case if the quasi-symmetric class and the topological class are the same. Okay? I have no idea if it's kind of a shame that I'm not able to answer this question for this simple kind of case, tand map. Okay?
Wait, but you do have this in subclass, right?
Yeah, so for these kind of things, you need to have really a discontinuity of the map.
Like an actual discussion.
Yeah, a jump. You need to have a jump. Okay. So in this case, you don't have jumps, and I don't know in this case if there's another obstructions that it implies.
What do you expect?
Yeah, that's a good question. I don't know. I thought a lot about it, and I think in some cases the post-critical set is quasi-symmetric rigid, but not the whole. It seems that not the whole phase space is quasi-symmetric rigid. So I don't know the answer actually. I don't know. Okay? So I just know about the condimension that the quasi-symmetric class is a Banach manifold finite condimension when all the points are eventually periodic. All the turning points, all the critical points, or the discontinuities are eventually periodic on the right and on the left. Okay? So it's a very specific situation. It's not. But it's surprising that even in this simple situation, you have difference between the two things. Yeah.
So some of the regularity, are you assuming that
Say again? In the discontinuities, yes. So I'm supposed that the limiting behavior on the right and on the left are periodic. Okay? On the right side, you go to some periodic point, and the left side, you also go to a periodic point. For the for the topological class, not for the topological class is completely general. For the quasi-symmetric class, that I don't know. Okay. Okay. So what's the next steps? The next steps is that this example is nice because you cannot use complex dynamics. I don't think you can use complex dynamics with these maps with discontinuities. I don't know. If someone can do it, but I can't. So it's nice that you can use similar arguments using similar to holomorphic motions to solve these questions, understand the topological classes of these guys. But it's not a very complicated kind of dynamical system. So the idea is to try to extend this theory for no expanding maps, so maps with critical points. And I believe that the main gradient will be ergodic theory. Okay? So let's say a good target would be to understand the topological classes of Cole-Ekman maps, for instance, where the order of the critical point is not an analytic point in the map. Okay? So we have some no flat critical point, but not analytic critical point. And I think, I guess that the tools will be using towers and inducing schemes to get rid of the critical point and solve the cohomological equation in some way. Okay, so we have some preliminary results for Cole-Ekman maps. So we have this result with Viviane Baladi, where I have unimodal maps with no flat critical points, just one critical point that's no flat, and Cole-Ekman satisfies some Benedicts-Carlson condition. Okay? So in this situation, if the cohomological equation has, for V in a codimension 1 subspace, this cohomological equation has a continuous solution, okay? But we don't know if it's better than that. So we have no idea how to prove that's more regular than that. And you use towers to prove this result. So I think that's it. Thank you very much for your attention.